time to start doing some problems here for area moment of inertia. And if you were to look in your book or if you various handbooks, you will find tables for certain specific shapes given axes where they will tell you the area moment of inertia for those shapes. So let's put that to use. So your book would have this. Here's a circle. If you look at x and y, the shape is symmetrical relative to them. So Ix and Iy should produce the same result, and in fact they do. So it's right here, 1/4 pi r to the fourth. And a rectangle, there's two very common places we could have a coordinate system. It could be based in the centroid, or it could be tied to the edges here, like so. And so for that case, I of little x, this is where your x-axis is, it's 1/12 base times height cubed. If you move it down to this edge, like so, it becomes 1/3 base times height cubed. So these are just standard things, and if you do enough of this, you'd have them memorized. So let's look at doing our first computation. So we're going to be looking at a rectangle with a hole in it. So that's what I have right here. Okay, we have a little hole in there, so it's 150 millimeters by 100. All right, with a 25 millimeter radius, that's the R, hole in this thing. And we want to get Ix. So X is down here. It's not up through here, it's here at the edge. Let's make that happen. And it's really straightforward. So I can look at this as being two pieces. It's this rectangle minus that hole. It's so just obvious. So the rectangle, well, we know exactly what that is. We can go up here. It's 1/3 base times height cubed. So 1/3, 100 times 150 cubed. Done. This is a hole, so we subtract it. Now, so the way you do these problems is you always start at the centroid and then you move it where you want to. Okay? So this hole, because it's a hole we subtracted, but just dealing with the hole, at centroid would be located along here. This would be the x-axis. So we start from this x-axis, which would be 1/4 pi 25 to the fourth, and then we move it to a parallel spot, namely right here. Okay, that has to be moved 75 millimeters. So the parallel axis theorem said it was d squared times area. D is 75. Square it. But what is the area of the hole? Pi r squared, where r is 25. So here it is based on the centroid, and then we move it 75 millimeters with the following area to get it down to here. Because it's a hole, we subtract it. Grab your calculator, 101 times 10 to the 6 millimeters to the fourth. If we put that in meters, it would be equally small number there as it's big here. All right. Next one. So this is the shape we're going to look at next. Let's bring this down in. So I have like a piece of angle iron. So it goes down over like so. And you can see the various dimensions that are on this thing. And so I have a coordinate system that goes through. This is obviously the center of this thing. So here's x, here's y from here, point going up. All right. So this stuff is 100 millimeters thick. So here we have 400 millimeters, 500, 300. There's the thickness. Then symmetrically up 400 over 500 up 300. All right. So we have our angle iron, and the question is find the area moment of inertia about y. Okay. So I'm going to break this down into some parts because I'm not going to find this in all likelihood in a text, but I'm going to in a table. But I can find these nice little rectangles really easily. So here's my breakdown into parts. I'm going to make a part A and C, which are symmetric relative to the y-axis. And then here's a rectangle B. So rectangle B is 100 by 600, and these are 100 by 300. And so I've put everything down. X is my typical perspective of base. So I have base for A, 100 by 300, and likewise for C. Base is 100, up 300, so on and so forth. And you'll notice I have a thing offset. So when I go to compute these things, if I take A, its centroid would be over here. Okay, that's 250 millimeters off of the centroid of the overall object. So when I compute this, I need to compute it at A centroid and then move it over. Likewise with C, at its centroid and then move it over. B, its centroid is right aligned with the y-axis. I have no problems. So there is no offset to be concerned about. All right, so let's start with what are my basic equations. What we had before was at a centroid for Ix, this was, remember we had I little x, we had 1/12 base times height cubed. Now, so what would y be? From y's perspective, the height is the base and the base is the height. So that's what we're seeing here, 1/12 height times base cubed when I go to compute the y. It's just flipped. And that makes sense. All right, so let's move this up. So the IY is going to be a summation of the A part, the B part, and the C part. It's that simple. Okay? Let's look at the A part. So what I have, we had 1/12. Okay, this is going to be height. So height was 300. Base was 100. Everything's just flipped here because it's the y-axis cubed. And that's computing this at this thing's centroid. And then I'll move it over to the y that I care about. So from the centroid of A over to the centroid of the object. 250 millimeters squared times area of this thing, which is 100 by 300. Done. Now note, what I'll get to C in a moment, C is exactly the same thing. Same size, same offset, so we won't even have to think about that. But let's look at B now. B is aligned with this axis, so that'll make it real easy. So I'm going to have, relative to height base cubed, we have 1/12. The height of this is 100. The base of this, which will be cubed, is 600. And then here's part C, just repeated from A. Use a calculator to add it all up. You get 5.6 times 10 to the 9th. Bring that up for you. Millimeters to the 4th. And that problem's all done. Next time, we're going to start doing integration. So we'll catch you up in a few moments, I hope. Bye now.